At the hardware level, a computer is a physical machine composed of microscopic electronic switches designed to process data. This block diagram identifies the core physical anatomy required for computing: the CPU, memory, storage devices, and various input-output channels. These discrete components are tethered together by a communication subsystem called the bus, which handles electrical flow between the processor and its peripherals. The CPU requires two types of data retention to function. Volatile memory provides high-speed access but clears when powered off, while persistent storage holds data long-term so it can be reloaded as needed. This physical arrangement remains inert until it receives a specific set of instructions to direct the electrical flow through the circuitry. The only language a CPU natively understands is machine language, the absolute lowest level of instruction. Machine language consists entirely of binary data. As shown by this 16-digit string, these ones and zeros map directly to physical switches inside the CPU. Programming this natively is a tedious process. Even basic operations require manual entry of these codes. Because humans cannot easily parse long streams of binary, reading or modifying a complex program written in this format is nearly impossible for a developer. This highlights the disconnect at the center of computer science. Developers require descriptive, logical language to organize complex systems, but hardware can only trigger on binary voltage. To bridge this gap, computer science developed sequential layers of translation and abstraction. The first layer of abstraction is a program designed to coordinate the physical hardware pieces previously discussed. This manager is the operating system. In this hierarchy, it sits directly on top of the hardware as its primary interface. Application programs cannot interact with the CPU directly. They must issue a request to the OS, which then executes the command on the hardware. This layer includes familiar systems like Microsoft Windows, macOS, and Linux. While the OS manages the hardware, developers still need a human-readable format to write the applications that run on top of it. The first move away from pure binary was assembly language, which replaces ones and zeros with short English words. Because the CPU still only reads binary, assembly requires a translator program called an assembler to convert these mnemonic words back into machine code. However, assembly remains tied to specific CPU architectures. A program written for one type of processor will not function on another. High-level languages removed this hardware dependency by using syntax that is English-like, strictly logical, and completely abstracted from the physical machine. This example demonstrates the readability of high-level syntax compared to binary or assembly. Programming in this format drastically reduces development cycles because the code is significantly easier to learn, write, and modify. While high-level languages are easier for humans, they require a complex software pipeline to translate these English statements back into binary for the computer. There are two primary architectural methods for this translation: interpreting and compiling. Let's start with the interpreter pipeline. As shown here, an interpreter reads one statement from the source code, translates it, and executes it immediately. This allows a program to run almost instantly, though execution is slower because translation happens continuously in real time. The compiler pipeline uses a different mechanical approach. A compiler reads the entire source code up front and translates it into a complete, standalone machine code file. The execution phase only begins after this entire file has been generated. Compilers require more time for the initial translation, but the resulting program runs faster because the computer doesn't have to translate code while it executes. For your exam, remember the core distinction. An interpreter translates line by line, while a compiler translates the entire file at once. A major drawback of compilers is that the resulting machine code file is permanently locked to the specific operating system and CPU it was compiled for. Sharing that program with a different type of computer would require the developer to recompile the source code from scratch. Historically, developers had to choose between the speed of a compiler and the flexibility of an interpreter, until Java introduced a hybrid translation pipeline. Java was designed as a general-purpose language intended to eliminate hardware lock-in. To achieve this, Java was built to be architecture-neutral and portable. In Java's hybrid pipeline, the compiler does not produce native machine code. Instead, it translates source code into an intermediate format called bytecode. Bytecode is a machine-independent language that is not tied to any specific processor. To run this bytecode, the host machine uses the Java Virtual Machine, or JVM. The JVM acts as a localized interpreter. It reads the universal bytecode and translates it line by line into the specific binary instructions required by that host machine. This creates the write once, run anywhere capability. Because bytecode is neutral, a single program can run on any platform without being recompiled, as long as that platform has a JVM. Java shifts the task of hardware translation away from the developer and places it onto the host machine's virtual machine. We can trace this architectural process using a basic JavaScript. This human-readable text is the high-level source code written by the developer. When execution begins, the compiled bytecode directs the JVM to enter the main method. As it reaches the execution statement, the JVM translates the bytecode to command the operating system. The OS then passes that translated binary through the bus to the hardware, signaling the monitor to display specific pixels. This results in the final output, the text string successfully displayed on the console. From the physical silicon at the bedrock through the OS and translated by the JVM, this stack of abstractions is the exact process that permits bytecode to run on disparate hardware.